There is a number that cosmologists use, and it is not the size of the universe. It is the size of the part of the universe we can see. Those are two very different things, and almost nobody talks about the difference. The number is 93 billion light-years. That's the diameter of what's called the observable universe, the sphere of space from which light has had enough time to reach us since the beginning of everything. 93 billion light-years. Most people hear that and think, okay, that's big, beyond comprehension. But here's the thing, that 93 billion light-year bubble, physics strongly suggests it's surrounded by more universe, far more. In some models, infinitely more, and in an infinite universe, something strange becomes not just possible, but mathematically inevitable. There is, somewhere out there, another version of this room, another version of you, listening to the same voice, and the distance to find them has no name in any human language. That's where tonight begins, not at the edge of what we can see, but past it. The observable universe is not the universe, it's a horizon, and tonight we're going to talk about what physics, geometry and cosmology actually say lies beyond that horizon. Not science fiction, not speculation dressed up as science, the real stuff, the numbers, the models, the implications that cosmologists have spent careers sitting with. By the end of tonight, the word universe is going to feel like the wrong word, too small, too tidy. What's actually out there is something we don't have good language for yet, but we're going to try to get close. Tonight we're getting into what lives beyond the edge of the map. So let's start with the map. The number 93 billion light-years gets quoted in documentaries, repeated in textbooks, mentioned at the bottom of articles about the latest space telescope finding, and almost every time, it gets repeated without a footnote that should be standing right next to it in bold letters. That number is not the size of the universe, it's the size of the part of the universe that has had time to talk to us. Think about what that means. The universe is 13.8 billion years old. Light travels at a fixed speed, so if a galaxy is more than 13.8 billion light-years away, the light from that galaxy hasn't reached us yet. We don't know it's there. We won't know it's there, not because it isn't there, but because the photons it's sending out haven't arrived. They're still in transit. And depending on how the geometry of space behaves over the next few billion years, some of them never will arrive. So the observable universe is a sphere drawn around us by the speed of light and the age of the cosmos. We are at the center of that sphere. Every observer is at the center of their own sphere. The sphere is real, and the sphere has a limit, and the limit is not the edge of reality. The limit is just how far the messengers have gotten. Before we go any further, if what you just heard already surprised you, or if you have a feeling this is going to go somewhere you didn't expect, take a second to like the video or subscribe to the channel. It genuinely helps this channel reach people who actually want to think about this stuff rather than just scroll past it. No pressure, we're going to be here a while. Now, back to the edge of the map. So we have a sphere, a bubble of space defined by what light has had time to do, and the diameter of that bubble is 93 billion light-years. That number, by the way, deserves a second of attention on its own because it confuses people the first time they hear it. The universe is 13.8 billion years old. The observable universe is 93 billion light-years across. That doesn't add up at first glance. If light takes 13.8 billion years to reach us, shouldn't the observable universe be 13.8 billion light-years in radius, or 27.6 billion light-years across? Here's why it isn't. The universe is expanding, has been, the whole time. Space itself, the medium between galaxies, has been getting larger, so a galaxy that emitted its light 13 billion years ago wasn't 13 billion light-years away when it sent that signal. It was much closer. But while the light was crawling across space toward us at the speed limit, space itself was stretching. The light had to cross a road that kept getting longer. By the time the light arrived, the galaxy that sent it was no longer 13 billion light-years away. It was about 46 billion light-years away. Maybe more. Multiply by 2 for the diameter, and you get the 93 billion light-year number. The current best estimate for the diameter of the observable universe. It's bigger than you'd expect from a simple multiplication, because space has been doing its own work the entire time the photons were on their way. So that's our bubble. 93 billion light-years across. Inside it, there are about 2 trillion galaxies. That number, by the way, used to be 200 billion. We didn't underestimate by a few percent. We underestimated by a factor of 10. In 2016, a team led by Christopher Consolis went back through the Hubble data and reanalyzed it more carefully, and the count went up by a factor of 10 in a single revision. We have been underestimating the number of galaxies in the observable universe for decades, and the new number, 2 trillion, is itself still a lower bound. The number could be higher. It probably is. Each of those 2 trillion galaxies contains, on average, somewhere between 100 billion and 1 trillion stars. Around many of those stars, planets. Around some of those planets, conditions that could be hospitable. We don't know how many, we don't know what they look like. We just know the number of opportunities for chemistry to do something interesting is much, much larger than the human imagination can comfortably hold. And all of that, all 2 trillion galaxies and their stars and their planets and whatever's happening on any of them, all of that is inside the observable universe. The bubble, the 93 billion light-years, the part of the cosmos that has had time to send light to us. Now, here is where the picture changes. The universe is almost certainly larger than that, possibly much, much larger. Even the most conservative estimates, using only the measurements we've directly made of the geometry of space, suggest that the total universe is at least 250 times the volume of what we can see, not 250 times the diameter, 250 times the volume. That's a difference of about 6 times in radius, which means the actual universe could be at minimum several 100 billion light-years across. And that's the conservative number. The cautious interpretation, the number you arrive at by trying not to extrapolate beyond what you've measured. If you let the math run a bit further, you start seeing universes that are millions of times larger. Some models, which we'll get to, suggest the actual universe is infinite, without bound, no edge anywhere. Take a breath with that, because it's a real claim and it deserves to be sat with for a moment. Imagine you're standing inside a single room of a building so large you can't see the walls. You're holding a candle. The candle lights about 10 feet around you. From your position, in that pool of light, you can see floor and ceiling and a bit of furniture. Beyond 10 feet, darkness. You might be forgiven for thinking the room is 10 feet across. That's what the light shows you. That's the data. But the room isn't 10 feet across. The room is enormous, and you have no way to know it, because the candle doesn't reach that far. The candle is doing what candles do. It's just a small thing in a much larger space. The observable universe is that pool of candlelight. The candle, in this case, is the speed of light combined with the age of the cosmos. We can see as far as light has had time to bring us. Beyond that, the room continues. We just don't have a candle bright enough. There's a second way to feel this, and it comes from human history. For most of the time our species has been around, people on one continent had no idea the other continents existed. Someone in ancient Egypt didn't know there were people in what would become Peru. The Peruvians didn't know about the Egyptians. Each civilization had a complete map of the world as they knew it. The map showed everything that mattered: cities, rivers, neighbors, threats, allies. The map was by every metric they had, complete. And the map was wrong. Not wrong in the sense of containing errors, wrong in the sense of being a tiny, tiny fragment of the actual world, with no indication anywhere on the map that there was anything beyond its edges. The map didn't lie, it just stopped where the cartographer's knowledge stopped. The fact that the world continued past the edge was something the cartographer literally could not draw, because there was no information about it. We are in that position now. The observable universe is our complete map. It contains everything we know, every galaxy, every star, every photon we've ever measured, and in all likelihood, it stops at the edges of the cartographer's knowledge. There's more beyond. We can't draw it. We can only know that the drawing stops where it does because of the limits of light, not because the territory does. So here's where we are. We have a map. The map is 93 billion light-years across. The map contains 2 trillion galaxies, and the map is small, possibly very, very small. Not because it's a bad map, but because the territory is large in a way we don't yet have the tools to draw. Which raises the obvious question: if there's more universe beyond the map, what's stopping us from seeing it? Why can't we just build better telescopes, point them in the right direction, and look further? The answer is stranger than you might think, and it isn't a wall. If you wanted to find the edge of what we can see, you might think of it like a wall, a solid line in the sky. Past here, no further. Inside here, the visible. That's the intuition, and it's wrong in an interesting way. The edge of the observable universe is not a wall, it's a horizon, and horizons behave very differently from walls. A wall is something you could in principle walk around or climb over. Given enough time and resources, walls can be crossed. A horizon is different. A horizon is created by geometry. It's the line beyond which you can't see, not because something is blocking your view, but because of the shape of the space you're standing on. The horizon at the ocean isn't a wall. It's a consequence of the curvature of the Earth. You don't break through it by sailing faster. You just keep finding more horizon. The horizon moves with you. The cosmological horizon is a horizon in that same sense. It's not a barrier, it's a geometric consequence of how space-time is built. And here's the part that catches people. The cosmological horizon is not a temporary limitation. It's not waiting for us to develop better technology. It's not something we'll someday get past with bigger telescopes. The cosmological horizon is permanent, and it's getting worse. Let me explain what I mean. The universe is expanding. We've known this since Edwin Hubble's observations in the 1920s, when he noticed that distant galaxies were moving away from us, and the further they were, the faster they were moving away. The expansion was steady for a long time, in the sense that physicists had a coherent model for it. The universe started small, exploded outward in the Big Bang, and has been expanding ever since, slowing down gradually under the gravitational pull of all the matter inside it. That picture was wrong. In 1998, 2 teams of astronomers, working independently, measured the brightness of distant supernovae and discovered that the universe wasn't slowing down, it was speeding up. The expansion of space was accelerating. Something was actively pushing the universe apart, faster and faster, against the gravitational pull of all the matter, trying to pull it back together. That something got named dark energy, mostly because we had no idea what it was, and the name needed to sound serious. Dark energy makes up about 68% of the total energy content of the universe. By comparison, ordinary matter, the stuff that makes up stars and planets and people and everything else we can see and touch, makes up about 5%. Dark matter, a separate mysterious thing that gives galaxies their structure, accounts for the remaining 27%. So when you add it up, everything ever observed by science, every star and every galaxy and every atom in every catalogue ever assembled, is 5% of the universe's energy content. The other 95% is invisible to us. We can measure its effects, we can name it, we can build models that include it, we just can't see it. And one consequence of dark energy is that the expansion of the universe is accelerating, which means that distant galaxies are moving away from us faster than they used to be, which means that given enough time, some of them will be moving away from us faster than the speed of light. You might be wondering how that's possible. Doesn't relativity say nothing can move faster than light? Here's the technicality, and it matters. Nothing can move through space faster than light. But space itself can do whatever it wants. The expansion of the universe isn't motion through space. It's the medium of space itself getting bigger. Imagine a balloon with two dots painted on it. As the balloon inflates, the dots move apart. The dots aren't traveling. The dots are stationary. The thing between them, the rubber of the balloon, is stretching. The dots can't move faster than the limit on motion across the surface of the balloon, but the stretching itself has no speed limit at all. If the balloon expands fast enough, the dots can find themselves separating faster than any signal could travel between them. That's what's happening on cosmic scales. The dots are galaxies. The balloon is space. The balloon is expanding, and in some regions it's expanding fast enough that the separation rate between us and distant galaxies exceeds the speed of light. Now here's where it gets quietly unsettling. If a galaxy is moving away from us faster than light, then any light it's currently emitting can never reach us. It's already too far away, and the gap is growing faster than the light can close it. The galaxy is, in the deepest sense, out of contact. We can't see what it's doing now. Not in 100 billion years, not ever. The light is in transit, and the road keeps getting longer faster than the light can travel it. The distance at which this transition happens is called the cosmological event horizon. It sits at roughly 16 billion light years from us. Galaxies inside that distance we can still receive light from. Galaxies beyond that distance we cannot. Not because the light isn't coming, because the road between us and them is stretching faster than the light can keep up. And here's the part that, if you sit with it, starts to feel different. The cosmological event horizon is moving. The expansion is accelerating, which means more and more galaxies are crossing the horizon over time. Galaxies that used to be inside our event horizon, where we could still receive their light, are gradually being pushed outside it. Once they cross, that's it. The light they're emitting at that moment never reaches us. The light they emitted before, what we're already receiving, will continue to arrive, but it will get progressively more stretched, more redshifted, more diluted, until it fades below detectability. Imagine you're listening to a song playing on the other side of a very long room. You can hear it clearly. As the room slowly stretches, getting longer, the sound waves still reach you, but they arrive deeper, lower, quieter. Eventually, the room gets long enough that the sound is too faint to hear at all. The song is still playing, the musician hasn't stopped. You just can't pick it up anymore, and if the room keeps stretching faster than sound can cross it, even new notes the musician plays will never reach your ears. That's the universe. Galaxies that we can see today are at this very moment sliding toward the horizon. Some of them are already past it, others will follow. The expansion isn't stopping, the horizon isn't getting closer. The implication, if you let it sink in, is that the universe we can observe is shrinking relative to the universe that exists. The total universe stays the same size, or grows, or is infinite, but our window into it gets smaller over time. Each century, fewer galaxies are reachable. Each million years, a few more disappear past the horizon. The records are being erased, slowly, by our standards, but inevitably. Here's where the timescale gets striking. In about 150 billion years, all galaxies outside our local group will have crossed the event horizon. The local group is the small cluster of galaxies gravitationally bound to ours, the Milky Way, Andromeda, the Magellanic Clouds, a few dozen smaller satellites, about 50 to 60 galaxies in total, depending on how you count. That's what will be left to observe. A civilization in our galaxy, 150 billion years from now, would look out at the sky and see what looked like an island universe, just their own cluster of galaxies sitting in apparent emptiness. No evidence at all that trillions of other galaxies had ever existed. No cosmic microwave background, the afterglow of the Big Bang, because by then it would have been stretched so far that no instrument could detect it. The history of the cosmos would be unrecoverable. Their best cosmological theory would describe a universe made of about 60 galaxies sitting in eternal darkness. And they would be wrong. They would be living in a much larger reality, but the evidence for it would be on the other side of an unreachable horizon. Think about that for a second. There is a future civilization, possibly our own descendants, who will look out at the same night sky we look at and see something completely different. Not because the universe will have changed, but because the universe will have moved out of view. A letter sent from a city that's moving away faster than the postal service can travel will never arrive. That's the literal situation of light from the most distant galaxies. The letters are in transit. Some of them have been in transit for billions of years. The galaxies that sent them have already crossed the cosmological event horizon. The letters will get stretched, redshifted, faded, and eventually become undetectable. Some of them will never finish arriving. The road keeps getting longer. So that's our situation. We're not just looking at a finite, knowable patch of a larger universe. We're looking at a window that's closing. Slowly, by any measure that means anything to a human life. But on cosmological timescales, the closing is real, and it's already started, and there's nothing anyone can do about it. Not now, not ever. It's geometry, not engineering. This is the moment, somewhere around now, when people sometimes start to feel something. Not quite fear, not quite sadness, just a quiet recognition that what we're talking about isn't a metaphor. The universe is doing this right now. The galaxies are crossing the horizon. The map is, in the deepest sense, smaller every year. And it's not even a fast process by cosmic standards. The expansion is gentle. The accelerations are tiny. A galaxy that crosses the horizon doesn't do it in a flash. It approaches the horizon over billions of years, its light progressively stretched, until at some point the stretching becomes infinite and the connection breaks. From our side, you'd never see a dramatic moment. You'd see a galaxy slowly redden, slowly dim, and slowly fade out of view, the way a face fades when someone walks away into the dark. So the edge of the map is real, it's physical, it's permanent, and it's not even in the long run a stable feature. It's an edge that closes in over time. That's the cosmological horizon. Now we have to ask the next question, and it's the bigger one. How big is the territory beyond the edge? For that, we have to talk about geometry, because the shape of space on the largest scales tells us almost everything we need to know about whether the universe has an end somewhere, or whether it just continues without bound forever. The geometry of the universe is a strange thing to think about, because we usually think of geometry as a feature of objects. Triangles have geometry, spheres have geometry, the space inside a building has geometry, but space itself, the empty backdrop in which everything sits, also has a geometry. And the geometry of space at the largest scales determines whether the universe has an end or not. Here's the simplest way I can put it. There are three possibilities for the geometry of space on the largest scales. The universe could be positively curved, like the surface of a sphere. It could be negatively curved, like the inside of a saddle, or it could be flat, like an infinite sheet of paper. Those are the three options, and each one has dramatically different implications. A positively curved universe is finite. If you travelled in a straight line long enough, you'd eventually come back to where you started, just like walking around the surface of the Earth. The Earth's surface is finite, but it has no edge. There's no wall at the end of the Earth. There's just more Earth eventually curving you back. A positively curved universe behaves the same way. It would have a fixed total volume, a definite calculable amount of stuff inside it. You couldn't get lost forever, because eventually you'd just come back. A negatively curved universe is infinite, and weird in ways that are hard to picture without doing some math. The angles of triangles add up to less than 180 degrees. Parallel lines, if you extend them far enough, diverge, The geometry feels wrong because human intuitions evolved on roughly flat ground, but it's a perfectly valid geometry, and it extends without bound. A flat universe is also infinite in the simplest version. It's an infinite plane, extended in all directions. Parallel lines stay parallel. Triangles add up to 180 degrees. The geometry feels normal because it's the geometry we live in at human scales, and it has no edge. It goes on in every direction forever. For most of the 20th century, physicists couldn't tell which of these three geometries our universe actually had. They knew the question was answerable, in principle, by measurement, but the measurements were hard. The measurement that finally settled it came from the cosmic microwave background. The cosmic microwave background is the afterglow of the Big Bang. About 380,000 years after the universe began, the cosmos cooled enough that hydrogen atoms could form, and the previously opaque plasma of free particles became transparent. The light from that moment has been travelling through the universe ever since. It's now stretched into the microwave part of the spectrum, which is why we call it the microwave background. It fills the sky in every direction. If you tuned an old analog television to a channel that wasn't broadcasting, a small fraction of the static you saw was that ancient light. The cosmic microwave background has tiny variations in temperature across the sky, hotter spots and cooler spots by very small amounts, less than 1 part in 100,000. A lake so perfectly still that even a single molecule of water moving on one end doesn't create a ripple detectable on the other. That's how uniform the early universe was. We'll come back to why that uniformity itself is significant. For now, what matters is the size of those spots. The size of the hot and cold spots in the cosmic microwave background depends on the geometry of space. In a flat universe, they appear at a particular angular size on the sky. In a positively curved universe, they look bigger because the curvature acts like a lens that magnifies them. In a negatively curved universe, they look smaller. When the Planck satellite measured the cosmic microwave background in detail, with the most precise instruments ever built for this purpose, the spots came out at exactly the size predicted by a flat universe, to within 0.4% precision. That's the number you'll see quoted. The universe is geometrically flat to within 0.4%. That doesn't mean it's perfectly flat. It means that if it has any curvature at all, the curvature is so subtle that it's below the threshold of what the most precise measurements ever made can detect, which is a useful way to know how flat something is. It's at least as flat as we can measure, and we can measure pretty flat. So we have a flat universe. Now, what does that mean for the size of it? A perfectly flat universe is infinite. By definition, a flat plane has no edge. It extends forever. If our universe is truly flat, then it's infinite in extent. No edge, no center, no bound anywhere. If it's almost flat but slightly curved, then it's finite but enormous. The shallower the curvature, the larger the universe before it curves back on itself. With curvature as small as we've measured, the universe would still have to be hundreds of times larger than the part we can see, at minimum. So even in the conservative case, where the universe has just enough curvature to be finite, but it's hiding below our detection threshold, the universe is much larger than our observable patch. Much, much larger. And in the most likely case, where the universe is perfectly flat or arbitrarily close to it, it's infinite, without bound, just more in every direction, forever. Take a moment with that. The universe is most likely infinite, not figuratively infinite, not unimaginably large, actually infinite, endless, without bound. Here's where it gets interesting, and where the mathematics start to do something strange. If the universe is infinite, and matter is distributed roughly uniformly throughout it, which all the evidence suggests it is, then something has to happen. Because the number of possible arrangements of matter in any given volume is finite. Let me explain why. Quantum mechanics, combined with general relativity, places a hard upper limit on the amount of information that can be contained in any given region of space. The limit is called the Bekenstein bound. It was first calculated by the physicist Jacob Bekenstein in 1981, working out the implications of black hole thermodynamics. The Bekenstein bound says that the maximum amount of information you can pack into a region of space is proportional to the surface area of that region, not the volume. Which is weird, by the way. We'll get to why it's weird. For now, what matters is the number. For a region the size of our observable universe, the Bekenstein bound says the maximum number of distinct configurations of matter and energy is approximately 10 to the power of 10 to the power of 123. That's a 1 followed by 10 to the 123rd zeros. Enormous. Beyond all human comprehension. Larger than the number of atoms in the observable universe by an unimaginable margin. But finite. That's the crucial word. The number of possible distinct states a region of space the size of ours can be in is enormous, but finite. There's a ceiling. There are only so many ways to arrange the matter and energy. You can count them. The number is huge. The number ends. Now combine that with an infinite universe. If the universe is infinite and matter is distributed throughout it, then it contains an infinite number of regions the size of ours. Each of those regions is in some configuration. The number of regions is infinite. The number of possible configurations is finite. By the pigeonhole principle, which is one of the most basic results in mathematics, if you have infinitely many regions to fill, and only finitely many possible configurations to fill them with, then some configurations must repeat. In fact, every possible configuration must repeat, infinitely many times. So somewhere out there, in the infinite universe, there's a region exactly identical to our observable universe, every galaxy in the same position, every star in the same position, every planet in the same position, every person in the same room listening to the same voice, every photon in the same place, every atom in the same quantum state. Not similar, identical. And not just one of them, infinitely many. Here's the way I sometimes try to think about this, and it doesn't quite work, but it gets close. If you shuffle a standard deck of 52 cards, the number of possible arrangements is about 8 followed by 67 zeros. A massive number, larger than the number of grains of sand on Earth, or the number of stars in the observable universe. If you shuffled the deck once a second for the entire age of the universe, you wouldn't get through a millionth of a millionth of a millionth of the possible arrangements. The number is, by any human measure, effectively endless. And yet, it's finite. There are 8 followed by 67 zeros possible arrangements, and that's all. If you shuffled the deck infinitely many times, every arrangement would come up, infinitely many times, including the arrangement where the cards come out in perfect order, ace through king of each suit. It would happen infinitely often, because finite divided by infinite is 0, and infinite multiplied by anything finite and non-zero is still infinite. The universe, if it's infinite, is doing this with regions of space instead of with cards. The deck of possible configurations of matter in a Hubble volume is enormous but finite. The shuffling is happening across the infinite extent of space rather than across time. The result is the same. Every possible configuration appears, infinitely many times. Including ours, including this exact room, including this exact voice, including, in some sense that's hard to wrap your head around, this exact you. We'll come back to what that means in detail later. For now, just sit with the math, because it's worth sitting with. The math doesn't say copies of you might exist. The math doesn't say there's a chance copies of you exist. The math says that if the universe is flat and infinite, copies must exist. Mathematically, necessarily, without choice. You can dispute the universe being flat, You can dispute it being infinite. Those are real questions, and they're not yet settled with certainty. But if you grant flatness and infinity, both of which are strongly supported by current evidence, then the rest follows, the copies follow. The repetition follows, the strange new shape of reality follows. There's a different way to see this, one that doesn't depend on cards or shuffles. Imagine driving on a perfectly flat highway. No curves, no coast, no cliff. You assume the road eventually ends. You assume that given enough miles, you'd hit something. A coast, a mountain range, an ocean, a wall, something. But in a flat, infinite universe, the road just continues. It doesn't curve back, it doesn't end, it just keeps going. Same kind of road, same kind of country, different specific scenery, but the same underlying structure, repeating, on, with no destination. In a flat, infinite universe, that's what space is doing, continuing, without bound, without end, with matter in it, doing the same kinds of things it does here. Galaxies forming, stars burning, sometimes, occasionally, configurations of matter complex enough to ask the question, what's beyond the horizon? And that's just the first line of evidence. The geometry alone says the universe is probably infinite, and infinite means the repetition follows, but there's a second line of evidence, separate from the geometry, that points in roughly the same direction. It doesn't even require infinite space. It requires something that happened in the first trillionth of a second of existence, something we're now reasonably confident actually happened, even though we have no way to ever observe it directly. That something is called inflation, and it changes everything about how big the cosmos might be. The first moments of the universe are hard to talk about, because the words we have for them aren't quite right. A trillionth of a second isn't a duration that maps onto anything in human experience. Light, in that amount of time, travels a distance smaller than the diameter of a single proton. The blink of an eye is 1,000 trillion times longer than the entire period we're about to discuss. We can write the numbers down, but the writing doesn't make them mean anything in our bodies. Still, this is the period when the universe did most of its serious work. The shape of everything that came after, including us, was set in this brief window. And what happened in that window is so strange that physicists spent years arguing about whether it could be true. The model that explains it is called inflation, and it's one of the central pillars of modern cosmology. Here's the basic picture. The universe began, in some sense we don't fully understand, in an extremely hot, extremely dense state. For decades, the model that physicists used to describe what happened next was straightforward. The universe expanded outward, slowly cooled, formed particles, formed atoms, formed galaxies, and ended up looking like the cosmos we see today. The expansion was rapid at first, and then slowed down over time. That was the standard Big Bang model. It explained a lot, but by the 1970s, it had developed some serious problems. One of those problems was the uniformity of the cosmic microwave background. We talked about this a moment ago. The temperature of the cosmic microwave background is uniform across the entire sky to within 1 part in 100,000. Every direction you look, it's the same temperature, same density of energy, same statistical properties. That's bizarre, and here's why. The cosmic microwave background was emitted from different parts of the early universe. The light coming from the patch of sky to your left came from one region of space. The light coming from the patch of sky to your right came from a completely different region. Those two regions, when the light was emitted, were far enough apart that no signal of any kind could have traveled between them. They were causally disconnected. They had never been in contact, and yet they're at the same temperature, to within 1 part in 100,000. How does that happen? If two regions have never communicated, how do they end up with the same temperature? There's no mechanism. It would be like meeting two people who've never met each other, who grew up on opposite sides of the planet, and discovering they have the same childhood memories, down to the details, to a precision of 1 part in 100,000. You'd be deeply suspicious. You'd want an explanation. The Big Bang model, in its original form, had no explanation. The uniformity was just a feature, a boundary condition, something the universe started with, for reasons unknown. There was also a second problem, the flatness of the universe. We've talked about this too. The universe is geometrically flat to within 0.4%. That's astonishing. The equations of general relativity don't generically produce a flat universe. They produce a curved one in either direction, with the curvature growing over time. For the universe to be as flat as it is today, after 13.8 billion years of evolution, it had to start out flat to a precision of something like 1 part in 10 to the 60th, which is again the kind of precision that demands an explanation. You don't get that by accident. So there were two problems, the horizon problem, which is the uniformity, and the flatness problem, which is the geometry. The standard Big Bang model just had to take both as initial conditions, which is to say it didn't explain them, it assumed them. In 1980, a physicist named Alan Guth proposed a solution that addressed both problems at once. He suggested that in the first tiny fraction of a second of the universe's existence, space underwent a period of exponential expansion. Not just rapid expansion, exponential expansion, where the size of the universe doubled and then doubled again and then doubled again, dozens of times in a row, in an unimaginably brief window. The model came to be called inflation. Here's what inflation says happened. From approximately 10 to the minus 36th seconds after the Big Bang to approximately 10 to the minus 32nd seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26th. Some models suggest the factor was much larger, 10 to the 78th, maybe more. We don't know the exact number, but we know it was unimaginably big. Let's translate that factor of 10 to the 26th into something you can almost picture. If you took a proton, which is roughly 10 to the minus 15 meters across, and you expanded it by a factor of 10 to the 26th, it would become 10 to the 11th meters across. That's 100 billion meters, which is larger than the orbit of the Earth around the Sun. So in this analogy, in the time it would take light to cross less than the width of a proton, the proton expanded to be larger than our entire solar orbit, and that's the conservative version of inflation. The aggressive versions are much, much bigger. That's what happened to space, not to matter, not to objects. Space itself, the medium of everything, expanded by that factor in that brief window. And then inflation ended, or rather, inflation ended in our region of space, and the universe entered the slower, more dignified expansion we've been measuring ever since. This solves both problems beautifully. The uniformity problem disappears because, before inflation, everything in our observable universe was in causal contact. Everything was close together. Everything could communicate, exchange energy, come to thermal equilibrium. Then inflation stretched that small, uniform region into something much, much larger than what we can see today. So the uniformity we see across the sky now is just the uniformity of a tiny pre-inflation region, stretched. The flatness problem disappears too. Any curvature the universe had before inflation got stretched out, in the same way that a small wrinkle on a balloon disappears when you inflate the balloon. The bigger you blow up the balloon, the flatter any local patch of its surface looks. By the time inflation ended, whatever curvature the universe started with had been stretched into something so flat we can't detect it. That's why we measure flatness to within 0.4%. Inflation made it that way. So inflation is a beautiful idea. It explains things that otherwise just had to be assumed, and as observational evidence has accumulated, it's held up. The structure of the cosmic microwave background, in detail, matches what inflation predicts. The distribution of matter on the largest scales matches. The lack of certain features, like cosmic strings or magnetic monopoles, that the older models predicted, matches what inflation predicts as well. Most cosmologists today consider inflation an established part of the model. Not in the same way that we consider gravity established, but in the way that we consider a well-supported theory established. It's the best explanation we have, by a wide margin, for the features of the universe we observe. Now here's where inflation gets stranger, and where the implications start to expand. The simplest version of inflation says it happened, it ended, and now we're in the post-inflation universe. But as physicists work through the details, they notice something. Inflation, in most realistic models, doesn't end everywhere at once. It ends locally. In some regions of space, the conditions that drive inflation collapse, and the universe transitions to its current state with normal expansion and the formation of matter and structure. In other regions, inflation continues, and because inflation involves exponential expansion, the regions where it's still going on grow much, much faster than the regions where it has stopped. This is the foundation of a model called eternal inflation, which was developed in the early 1980s by Andrei Linde and independently by Alexander Vilenkin. Eternal inflation says that inflation, once started, never stops globally. It ends in pockets, bubbles. Each bubble is a region where inflation has decayed, and within that bubble, normal physics takes over, and you get a universe with stars and galaxies and all the usual stuff. Our observable universe is inside one of those bubbles, the bubble we're in. Outside our bubble, inflation continues. The space between bubbles is still expanding exponentially. New bubbles are forming all the time in regions where inflation locally collapses. Each new bubble is its own universe, in the sense that it has its own internal physics and its own internal time and its own observers, if any. The bubbles never communicate because the space between them is expanding faster than light. They're causally disconnected from each other, the same way galaxies beyond our event horizon are causally disconnected from us, but more so. If eternal inflation is correct, then the number of bubble universes is, for all practical purposes, infinite. Inflation has been going on, somewhere, since the beginning of everything, and it's still going on now, and it will continue going on, eternally. Bubbles keep forming. The total number of universes in this picture isn't a fixed quantity, it's growing. It's been growing forever, in some sense, because eternal inflation has no preferred starting moment. There's no beginning to the process in the usual sense. It's been happening, somewhere, throughout the entire history of whatever this larger structure is. Take a moment with that picture. Our universe, the 93 billion light-year bubble we can see, is one bubble. Around it, more bubbles. Around those, more. Between them, exponentially expanding space generating new bubbles all the time. The whole picture is sometimes called the inflationary multiverse, and it's a direct prediction of most well-developed inflation models. It's not an addition, it's not a speculation, it's what the equations of inflation say happens if you take them seriously and follow them through. Now you might be wondering, is that really science? If we can never see another bubble, never communicate with one, never get any direct evidence that bubbles other than ours exist, how is this different from speculation? It's a fair question, and the answer is that the multiverse in this picture is not what we're testing. What we're testing is inflation, the inflation that we can see evidence for in the cosmic microwave background, in the distribution of galaxies, in the geometry of space, gives us a model of physics. That model, when you apply it to the early universe, generates eternal inflation as a consequence. The multiverse is a prediction of a theory that has, on the parts we can test, performed well. We can't test the multiverse directly, but we can test the theory that predicts it, and the theory is, so far, holding up. Whether that's enough to convince you of the multiverse depends on your taste in inference. Some physicists are entirely comfortable with it, others want more direct evidence. The honest answer is that we don't know for sure. We have a strong model that predicts it. We don't have a direct observation. That's where the field is. Here's the picture then. Our universe is a bubble. The bubble is at least 93 billion light-years across in the part we can see, and almost certainly larger, possibly infinitely larger, in the part we can't. Around the bubble, more bubbles, between them, exponentially expanding space, with new bubbles forming continuously. The whole structure may have no beginning, no end, no edge. And here's the question that pulls us into the next part. If there are other bubbles, what are they like? Are they like ours? Do they have the same physics, the same particles, the same laws? Or are they different, in fundamental ways we have a hard time picturing? The answer, if the most successful models of string theory are right, is that they're different. Very different, strange in ways that change what the word universe even means. When we think about other universes, the natural assumption is that they'd be like ours. Different particulars maybe, different histories, different specific galaxies, but the same underlying physics, the same kind of place. That assumption is almost certainly wrong, if eternal inflation combined with string theory is anywhere close to correct. Here's the picture, in the most concrete form I can give it. String theory is one of the leading candidates for a unified theory of physics. It tries to explain all the fundamental particles and forces of nature as different vibrations of tiny one-dimensional objects called strings, operating in more than the 3 spatial dimensions we're used to. It's mathematically beautiful, and it has the property that it could in principle describe everything. The catch is that, when you work through the equations carefully, string theory doesn't predict one universe. It predicts a vast number of possible universes, each one corresponding to a different way the extra dimensions of space can be curled up. How vast? The current best estimate is that there are approximately 10 to the 500th distinct possible configurations. Each one is what physicists call a vacuum state. Each one represents a possible universe with different fundamental physics, different masses for the elementary particles, different strengths for the fundamental forces, different values for things like the cosmological constant which governs dark energy, different rules for how matter and energy behave. That number, 10 to the 500th, is sometimes called the string landscape, and it deserves a moment of attention because it's the kind of number that breaks human intuition entirely. The number of atoms in the observable universe is approximately 10 to the 80th, which is already a number so large you can't really feel it. You can write it down, you can manipulate it on paper, but you can't picture 10 to the 80th of anything. There aren't enough things in the world to picture. The string landscape contains 10 to the 500th possible universes. The difference between 10 to the 80th and 10 to the 500th isn't a difference of degree, it's not even close. 10 to the 500th is the number 10 to the 80th raised to a power of about 6, which is to say, if you took every atom in the observable universe and made each one stand for one universe in the string landscape, you'd still only have a tiny fraction of the total. You'd have 10 to the 80th universes accounted for. There would be more than 10 to the 420th more left over. Numbers like that don't sit in the same conceptual space as numbers we can think about. Comparing 10 to the 80th to 10 to the 500th is not like comparing 1,000 to 1,000,000. It's not like comparing 1,000,000 to 1,000,000,000. It's something different, something the human mind has no native handle on. The numbers are just symbols, doing what mathematics tells them to do. The string landscape contains 10 to the 500th possible universes. Now, what's a string landscape good for if you can't visit any of these universes? On its own, not much. But combined with eternal inflation, it becomes something else. Eternal inflation provides the mechanism for actually populating the landscape. Each bubble universe, when inflation locally ends, drops into one of the 10 to the 500th possible vacuum states. Which one depends on the specifics of the decay, which appear to be effectively random within the constraints of the model. Different bubbles end up in different vacuum states. Different bubbles have different physics. Some of those vacuum states are similar to ours. Some of them are wildly different. Most of them statistically are sterile. They don't permit the kind of complex structure we see in our universe. A bubble where the strong nuclear force is just slightly stronger. Hydrogen atoms can't form because the protons fuse into something heavier almost immediately. No hydrogen means no stars in the way we know them, no chemistry, no anything we'd call life. A bubble where the strong nuclear force is slightly weaker. Atoms don't form in the first place. The nuclei don't hold together. The universe is a soup of free particles with no structure beyond that. A bubble where the cosmological constant, the strength of dark energy, is just a little larger. The universe expands too fast for galaxies to form. Matter doesn't have time to clump under gravity before it gets stretched apart. No galaxies, no stars, no structure of any kind, just an ever-thinning gas dispersing forever. A bubble where the cosmological constant is even larger than that by a few orders of magnitude. The universe expands so fast that even atoms can't stay together. The particles in any forming structure just get torn apart by the expansion. Nothing complex ever happens. The point is, most of the 10 to the 500th universes in the string landscape are uninteresting, not interesting in the colloquial sense, uninteresting in the sense that nothing happens in them. They don't produce galaxies, they don't produce stars, they don't produce chemistry. They expand, they cool, they fade, and nothing in them ever asks why. A tiny fraction of those 10 to the 500th universes have parameters that allow complex structure to form. We're in one of them, and the values of the constants in our universe, like the cosmological constant, like the masses of the fundamental particles, like the strengths of the forces, are tuned very precisely to values that permit structure to exist. Here's the example that gets quoted most often, because it's the most striking. The cosmological constant in our universe is approximately 10 to the minus 29 grams per cubic centimeter, which is by any measure an absurdly tiny number. Almost zero, but not quite. The question, for decades, has been why. There's no obvious reason for it to be that small. Quantum field theory, the most successful theory of fundamental physics we have, predicts that the cosmological constant should be enormous, many orders of magnitude larger than what we observe, something like 10 to the 120 times larger. If the cosmological constant were that large, the universe would have expanded so violently in the early moments that no structure of any kind could have formed. No galaxies, no stars, no us, just a thin, ever-thinning gas, getting stretched apart faster than gravity could pull it together. So the question is, why is the cosmological constant so small? Why is it precisely what it needs to be for galaxies to form? In 1987, a physicist named Steven Weinberg made a prediction using the multiverse framework. He said, suppose the cosmological constant has different values in different bubble universes. Suppose it's effectively random across the string landscape. Then most bubbles have a cosmological constant too large to permit galaxies. Those bubbles are sterile. They don't have observers, so no one ever asks why the cosmological constant has the value it does in those bubbles. Only in bubbles where the cosmological constant happens to be small enough to allow galaxies to form, do you get the kind of complex structure that leads to observers, who then look around and ask why their universe has the parameters it does. Weinberg calculated the range of values for the cosmological constant that would permit galaxy formation. He predicted the cosmological constant in our universe should be small, but not zero, within a particular narrow range. In 1998, when we first measured the actual value of the cosmological constant from supernova observations, the value fell within Weinberg's predicted range. The multiverse model had made a quantitative prediction that was later confirmed by observation. That doesn't prove the multiverse exists. It's not the kind of confirmation that settles the question, but it's not nothing. It's one of the few cases where a multiverse model has produced a specific numerical prediction that was subsequently confirmed by independent measurement. Physicists notice when that happens. It's not the same as direct evidence, but it's evidence of a particular kind. The theory predicted something, the prediction came true, the theory survives another test. So the picture, if you take string theory and eternal inflation together, is this. Reality is not one universe. It's a landscape of 10 to the 500th possible universes, populated by the eternal inflationary process. Most of them are sterile, with parameters that don't permit complex structure. A small fraction have parameters that allow galaxies, stars, chemistry, observers. We're in one of those. The reason our universe has the parameters it does isn't that some deep principle requires it. It's that, in the small fraction of bubbles where observers can exist, the parameters have to fall in a particular range. We measure those parameters, and they confirm we're in one of the rare habitable bubbles. That's the multiverse picture, in its most worked-out form, and the implication for our purposes tonight is that the question how big is the universe doesn't have a single answer anymore. The universe we can see is 93 billion light-years across. Our bubble might be infinite. Beyond our bubble, more bubbles, with different physics. The total reality has a structure that doesn't map neatly onto our intuitions about what a universe is. Here's an analogy that helps me at least get a feel for this. Think about evolution. Evolution doesn't produce one organism and stop. It produces billions of variations, most of which don't survive. The ones that persist are the ones that happen to fit their environment. Looking at the variety of life on Earth, you don't say, "Why are there penguins?" You say, in the space of all possible organisms, some of them happen to have features that worked in their environment, and they persisted. Penguins persist because penguins fit. There's no deeper reason for penguins than that. The multiverse in this picture is doing something similar with universes. It produces an enormous variety, most of which don't permit complex structure. The ones that do persist, or rather, the ones that do have observers in them who notice that they exist. We're not in our universe because some principle required us. We're in our universe because the parameters happen to permit us. In other bubbles, with different parameters, no one is asking the question. There's no one there to ask. Here's another way to feel it. Different bubble universes are like signals on different radio frequencies. You exist on one frequency. The others are broadcasting all around you at all times, but you don't have a receiver capable of detecting them, and you never will. Not because the technology is beyond you, because the physics of your frequency makes detecting another frequency impossible by definition. The frequencies don't talk. The frequencies don't share a medium. The frequencies are causally disconnected by the structure of the model forever. So we have a vast multiverse, with most of it inaccessible, and we have within our bubble an infinite or nearly infinite extent, with implications about copies and repetition. Let's come back to those implications now, because they're worth sitting with. Here's a fact that I want to give you straight, without dressing it up. If the universe is flat and infinite, which the best measurements we have suggest it is, then somewhere out there, right now, there's another version of you. Not someone similar, not a parallel life cousin, an exact copy, every atom in the same place, every memory in the same state, every neuron firing the same pattern, listening to a voice in a room that looks exactly like this one, hearing this exact sentence at this exact moment with the same understanding. That copy is not theoretical, it's not metaphorical. It's a direct mathematical consequence of two assumptions that we have very good reasons to believe. The universe is flat. The universe is infinite. If both of those are true, then copies are not a possibility. They're a requirement. Let me walk through why carefully, because the reasoning is worth following. We talked earlier about the Bekenstein bound, the limit on how much information can be packed into a given region of space. For a region the size of our observable universe, the number of possible configurations of matter and energy is enormous but finite, approximately 10 to the 10 to the 123rd, which is a number we can write but not picture. What matters is that it ends. There are only so many possible arrangements of stuff in a region this size. The count is huge. The count is also a real number. Now, if the universe is infinite, then there are an infinite number of regions the size of ours. Each region is in some configuration. There are infinitely many regions and finitely many possible configurations. By the pigeonhole principle, some configurations must repeat. In fact, every possible configuration must repeat, infinitely many times. The physicist Max Tegmark, who has spent much of his career thinking through these implications, calculated the typical distance to the nearest exact copy of our observable universe. Every particle in the same place, every quantum state identical. He arrived at a number. The number is 10 to the 10 to the 29th meters. I want to sit with that number for a moment, because it's the one number in this whole script that doesn't have a useful human comparison. Most numbers, no matter how large, can be brought down to Earth with the right analogy. This one can't. The number 10 to the 10 to the 29th meters has more digits in its exponent than there are atoms in the observable universe. The exponent alone, written out as a decimal, would require more material than we have access to in any sense. There's no comparison. There's no stack of coins, no string of pearls, no relay of cars driving end to end that gets you anywhere close. The distance to the nearest exact copy of our observable universe is, in every meaningful sense, beyond any comparison the human mind has access to. We can write the number, we can manipulate it, we can use it in calculations, we cannot picture it. That's where the nearest exact copy of our observable universe sits. Somewhere out there, at that distance, every particle in our observable universe has a duplicate. Every star, every galaxy, every person. The nearest copy of you specifically, just you, not the whole observable universe, is closer, considerably closer by the standards of these numbers, but still vast, still beyond comparison. Tegmark estimated the typical distance to a region exactly like the one immediately around you, say a 100-meter cube containing the same air molecules in the same positions, the same dust on the same surfaces, the same person in the same chair, at something like 10 to the 10 to the 91 meters. Smaller exponent, still uncountable. So there's a copy of you, in a copy of this room, hearing a copy of this voice, at a distance with no name in any human language, not just one, infinitely many. The number isn't large, it isn't enormous, it's infinite. And here's the part that for me makes this material different from most cosmology. The copies aren't generic. They aren't versions of you with the same general shape and slightly different memories. They are to the level of every quantum state of every particle, identical. Same brain, same body, same neurons firing, same words being processed, same understanding being formed. Some of those copies have made every decision you've ever made identically. Some of those copies will, tomorrow, continue making the same decisions you make. Some of them won't. The number of copies whose lives have proceeded exactly in parallel with yours, up to this exact moment, is infinite. The number of copies who will continue to do so for the next minute is infinite. The number who will diverge from you tomorrow, in one particular way, is infinite. The number who will diverge in any other particular way is also infinite. You are not singular in the strictest mathematical sense if the universe is flat and infinite. You're not unique, you're not even rare. You are one instance of an infinitely populated configuration. Let me give you a way to feel this that doesn't lean on the math. Jorge Luis Borges wrote a story in 1941 called The Library of Babel. The library, in his story, contains every possible book, every combination of letters, every possible story, every possible history. Most of the books are nonsense, just random sequences of letters with no meaning. But somewhere in the library is every book that has ever been written, every book that could be written, including a book that's the exact biography of your life, including a book that's the same biography with one word changed, including a book that's your biography but with a different ending. The library contains them all. Borges meant it as a metaphor. He was making a point about meaning and randomness and the human search for significance. In an infinite flat universe, That library is not a metaphor, it's the universe itself. Every possible book exists, on a shelf, somewhere, at some incomprehensible distance. The book of your life exactly as you've lived it, written and shelved. The book of your life with one different choice tomorrow, written and shelved. The book of every life you didn't lead, every variation, every possibility, all of them, sitting on shelves, in rooms you'll never visit. Borges imagined the library as a great labyrinth. The infinite universe makes the labyrinth literal. The corridors stretch in every direction, with no end. The shelves continue, the books continue, the lives continue, all of them somewhere, exactly happening, exactly being read. Or here's another way. Think about photographs. A photograph contains a finite amount of information. A digital image is just a grid of pixels, each pixel set to one of a finite number of color values. The total number of possible images at a given resolution is enormous but finite. You can calculate it. For a typical photograph, the number is somewhere around 10 to the millions, huge, but finite. That means, in principle, there are only so many possible photographs. Every photograph you've ever taken, every photograph anyone has ever taken, every photograph that will ever be taken, exists somewhere in the space of possible images. Most of the possible images would look like static, like random noise. A vanishingly small fraction would look like coherent scenes. Within that fraction, an even smaller fraction would look like recognizable subjects. But the total set is finite. If you were given enough random photographs, you would eventually generate every possible image. The picture of your wedding, the picture of your grandmother as a child, the picture of you on your last day, in some future you haven't lived yet. Every picture exists in the space of possible images, and given enough samples, you'd find all of them. The infinite flat universe is doing something like this with regions of space. The total set of possible configurations of matter in a Hubble volume is finite. The number of Hubble volumes in an infinite universe is infinite, so every possible configuration appears infinitely often. Max Tegmark, who I mentioned earlier, classifies multiverses into 4 levels. We've actually been moving up the levels as the script has gone on, even though I didn't flag it that way. A level 1 multiverse is just an infinite flat universe. Same physics everywhere, same laws, just more space, more matter, more of the same. Inside a level 1 multiverse, the repetition we've been discussing happens. Copies of you exist, copies of this room exist, copies of this exact conversation exist. Everything that can happen, given the laws of physics we observe, happens infinitely many times. A level 1 multiverse requires no new physics. It follows directly from flatness and inflation, both of which are strongly supported by observation. A level 2 multiverse is the inflationary multiverse we talked about. Different bubble universes with different physical constants. Some of them are like ours, most of them are very different. The level 2 multiverse is also strongly suggested by the combination of inflation and string theory, but the evidence is more indirect. A level 3 multiverse comes from quantum mechanics. It says that every time a quantum event has multiple possible outcomes, all outcomes actually happen in separate branches of a wave function that don't communicate with each other. Hugh Everett proposed this in 1957. It's a controversial interpretation, but it's not crazy, and a non-trivial fraction of physicists think it's the right interpretation of quantum mechanics. If it is, then every possible quantum branch contains a different version of everything, including you. We don't have time to go deep into this one, but it's worth knowing it's there. A level 4 multiverse is the most radical. It says that every self-consistent mathematical structure exists as a physical reality. We'll come back to this one in a moment. It's the deepest of the multiverses, in the sense that it requires the most metaphysical commitment. But it's also the cleanest, in the sense that it doesn't draw arbitrary lines between what exists and what doesn't. For now, what matters is that even the most conservative of these levels, level 1, gives you copies. The argument is robust. It doesn't depend on speculative physics. It depends on flatness, infinity, and the Bekenstein bound. All three are well established. The conclusion follows. So when you hear someone say, the universe is so large there must be life out there, what they're gesturing at is a special case of a much larger statement. The universe, if it's flat and infinite, contains every possible thing, infinitely often. Life is the least of it. Galaxies you'd recognize, conversations you've had, rooms you've sat in, faces you've loved, all of them, somewhere, infinitely many times. That's what an infinite flat universe means. Not just bigger, not just more. Endless repetition of every possible thing, every story already told, somewhere, in the same words with the same ending. Every variation already lived, somewhere, by something exactly like you. Take whatever feeling that lands as. There's no right reaction to this material. Some people find it terrifying. Some people find it comforting. Some people find it absurd and refuse to take it seriously, which is also a reasonable response. The math is what the math is. The implication follows from the assumptions. The assumptions are well supported. That's where we are. Now we have to go one level deeper. Because we've been talking about the universe in terms of matter and energy and space. But there's an even deeper version of this question. One that asks not how big the universe is, but what the universe is at its most fundamental level. And the answer that some physicists are starting to take seriously may be the strangest answer yet. Most of us, when we think about mathematics, think of it as a tool, a language, a set of symbols that humans develop to describe the world. We think 2 + 2 = 4 is a fact about the world, and mathematics is the way we talk about that fact. The world is the real thing. The math is the description. There's an old idea, going back to Plato and beyond, that maybe this gets the relationship backwards. Maybe mathematics isn't the description of the world. Maybe mathematics is the world. Maybe what we experience as physical reality is, at its most fundamental level, just mathematical structure, instantiated. The Platonists thought of mathematical objects as the only real things, with physical objects being shadows of the mathematical forms. Modern physicists who hold a version of this view don't usually use the language of Plato, but the core idea has some life in it. Max Tegmark, again, has been the most vocal modern proponent. He calls his version the mathematical universe hypothesis. The hypothesis is short, and once you state it, the implications are huge. The hypothesis says that physical reality is, identically, a mathematical structure, not described by one, is one. There's no separate physical substance that gets described by math. The math is the substance. Reality is the mathematical structure itself, being what it is. If that's true, then the question of what exists becomes a question about mathematics, and the answer becomes radical. Every self-consistent mathematical structure exists as a physical reality, in the same sense ours does. The number of self-consistent mathematical structures is, in any meaningful sense, infinite. So reality in this view is far larger than even the inflationary multiverse. The string landscape with its 10 to the 500th universes is a tiny corner of a much vaster mathematical landscape. A landscape that includes universes with physics we have no concept of, with structures that don't even fit into our category of universe. Tegmark calls this his level 4 multiverse. Everything mathematical, everything coherent, all real, in the same sense our universe is real. Now, is there any reason to take this seriously, or is it just metaphysics dressed up in equations? There's a reason, and it's a real one, even if it doesn't quite prove the case. The reason was named in 1960 by the physicist Eugene Wigner. He wrote a famous essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. The title says most of it. Wigner pointed out that mathematics, when applied to physics, works strangely well, much better than it has any right to. Here's the puzzle. Mathematicians frequently develop new mathematical structures for purely abstract reasons. They're not trying to describe the physical world, they're following the internal logic of mathematics, exploring what's interesting, what's beautiful, what's coherent. Sometimes the structures they develop are deeply weird and seem to have no possible application. Then, sometimes decades later, a physicist looking for the right language to describe some new experimental findings stumbles into one of those abstract mathematical structures and discovers that it fits perfectly. The structure that the mathematician developed for no physical reason turns out to be the exact mathematical language of some physical phenomenon. This has happened repeatedly throughout the history of physics. Riemannian geometry is the most famous example. Bernhard Riemann developed it in the 1850s as a purely abstract extension of geometry to curved spaces. He had no idea what it would be good for. It was mathematics for its own sake. 60 years later, in 1915, Albert Einstein needed a mathematical framework to describe gravity as the curvature of space-time. He went looking for the right kind of math, and there was Riemann's geometry waiting. The fit was perfect. Einstein didn't have to invent the math, he just had to find it. Imaginary numbers are another example. Mathematicians introduced them reluctantly in the 16th century to solve certain kinds of equations. They were considered an embarrassing trick for a long time. The word imaginary was meant pejoratively. Then, in the 20th century, when physicists developed quantum mechanics, imaginary numbers turned out to be essential. The wave function, which describes the state of a quantum system, is complex-valued. It uses imaginary numbers in a fundamental way. Without imaginary numbers, you can't even write down the equations of quantum mechanics. The mathematicians who invented imaginary numbers had no idea this would happen. They were just doing math. Group theory, similarly, was developed in the 19th century to study the symmetries of equations. It seemed like a niche tool. Now it's the language we use to describe every fundamental particle in nature. The standard model of particle physics is at its core a group theory model. The particles are representations of certain mathematical groups. The forces are gauge symmetries of those groups. The whole structure of fundamental physics turns out to be group theory, even though group theory was developed for entirely different reasons. The pattern repeats. Topology, differential forms, fiber bundles, complex manifolds, each one developed by mathematicians for mathematical reasons, each one later turning out to be the exact right language for some physical phenomenon. Wigner found this strange. Mathematics is supposed to be something we make up. Physics is supposed to be something we discover. How does the thing we make up keep turning out to be the thing we discover? There are different possible answers. One is that mathematicians have good taste, and they develop the structures that are likely to be useful. That's part of it, probably, but it doesn't explain the cases where the math was developed in advance, with no physical motivation, and later turned out to fit. Another answer is coincidence, but the number of coincidences is now large enough that this answer doesn't satisfy most people. Another answer is that physicists are unconsciously biased toward formulating theories in mathematically elegant ways, so they find the math that's already there. There's something to that, but again, it doesn't explain everything. The strongest version of the answer, the one Tegmark is making, is that mathematics doesn't merely describe physics. Mathematics is physics. The reason mathematical structures keep fitting physical reality is that physical reality is a mathematical structure. They're the same thing. The puzzle of unreasonable effectiveness dissolves because there's no longer anything to be effective at. The math is just what's happening. If you take that idea seriously, then physical reality isn't limited to the things our particular mathematical structure describes. Every consistent mathematical structure is its own physical reality, just as real as ours, just as full of stuff, just as populated by whatever observers it can support. The set of all consistent mathematical structures is in some sense the set of all possible realities, and that set is large in a way that makes even the inflationary multiverse look small. Here's the analogy that I find useful. Think about a dream. A dream feels fully real while you're in it. The world of the dream has a kind of physics. It might be a weird physics, where you can fly, or where time runs backward, or where you keep arriving in places you didn't intend to go. But within the rules of the dream, things behave consistently. You don't experience the dream as a description of a world. You experience the dream as the world. The dream is a self-contained mathematical structure, in some sense being instantiated by a brain. The mathematical universe hypothesis says the difference between your dream and your waking life is not that one is real and one is simulated. It's that one is more computationally complex than the other. Both are, in the deepest sense, mathematical structures being instantiated. Your waking life happens to be a particularly elaborate one, with lots of consistent rules and lots of detail. Your dream is a simpler one, less consistent, less detailed. But the difference is one of degree, not kind. Both are mathematical structures. Both are real, in the sense that they're being instantiated and experienced. That's a strange place to end up. Most people, when they encounter this idea for the first time, feel something between confusion and irritation. It seems like the kind of thing that's just words. Mathematics, in our normal experience, is symbols on a page. The world, in our normal experience, is full of things we can touch and taste and hold. They don't seem like the same kind of stuff. How can mathematics be the world? The honest answer is that we don't know if the mathematical universe hypothesis is correct. It's a hypothesis. It's not testable in any direct way. It's a framework for thinking about reality that some physicists find appealing because it makes the unreasonable effectiveness of mathematics reasonable. It's not, at the moment, a settled scientific conclusion. It may never be, but it's worth knowing it's out there as one of the more radical answers people have given to the question of what's actually going on. If the mathematical universe hypothesis is correct, then the question we've been circling all night becomes much larger. We started with the observable universe, 93 billion light-years across. We expanded to the larger universe, possibly infinite. We expanded to the inflationary multiverse, with 10 to the 500th bubble universes. And now we're asking whether all of that is itself just a small corner of an even vaster reality of all possible mathematical structures, all of them being instantiated, all of them just as real as ours. It's a lot. It's worth letting it be a lot. Here's something I want to say plainly before we move on. None of this material is meant to make you feel small. People often hear about the size of the universe and the possibility of the multiverse, and they react with a kind of vertigo. They think, what's the point of anything I do if there are infinite copies of me doing it? What does it matter what I choose if all choices are being made somewhere? What's the meaning of my life if my life is one instance of an infinite repetition? Those questions are real. I don't want to brush past them, but I'll say this. The fact that the universe is large doesn't take anything from you. The size of the universe was not previously small. The universe was always this big, or this many, whichever turns out to be true. We just didn't know. The discovery that we live in a vast reality doesn't make us smaller. It changes our picture of where we are. It doesn't change us. You're still here. The voice in this room is still here. The decision you make tomorrow is still yours, even if some version of you somewhere is making a different one. The choices in front of you still belong to you. The vastness doesn't take any of that. So that's the deepest version of the multiverse idea. Mathematics as reality. All consistent structures as real. A reality bigger than anything physics alone can describe. Whether or not it's correct, it's worth knowing about. It's a real proposal, taken seriously by serious people. Let's come back now to what's actually in front of us. The universe we can see. Because even within our observable patch, even within the part of reality we have direct access to, there's structure that's worth pausing to look at. Structure that, when you understand it, makes you feel something different about where you are. When you look up at the night sky, the stars look scattered, random. some thicker in patches, some sparse, but no obvious pattern. If you didn't know better, you'd think the universe was just stars and galaxies spread out in space, distributed without organization, like sand on a beach. That's not how it looks at the largest scales. When astronomers map the positions of galaxies across the entire observable universe, what they find is structure, not random scattering, a pattern, a vast, intricate three-dimensional network that looks in the simulations and the survey data like an enormous web. Astronomers call it the cosmic web, and the name isn't a metaphor. The structure really does look like a web, bright filaments of matter, connecting at nodes where galaxies cluster, separated by vast empty regions where almost nothing is. The filaments are long strands of galaxies stretched across hundreds of millions of light years, hundreds of thousands of galaxies threaded along each strand. At the junctions where filaments cross, you get galaxy clusters, dense concentrations of gravitationally bound galaxies, sometimes thousands of them, in regions that are by cosmic standards small. Between the filaments, the cosmic voids, enormous bubbles of nearly empty space, hundreds of millions of light years across, with very few galaxies inside them. This structure didn't form by accident. It's the direct result of tiny variations in the density of matter in the very early universe. When the cosmic microwave background was emitted 380,000 years after the Big Bang, the universe was almost perfectly uniform. The variations in density across the sky were less than 1 part in 100,000. Tiny differences. The hotter spots, slightly denser. The colder spots, slightly less dense, almost nothing, by any human measure of difference. But gravity is patient. Over billions of years, the slightly denser regions pulled in more matter. The slightly emptier regions lost matter to their denser neighbours. The differences grew. After 13.8 billion years of this slow accumulation, the original 1 part in 100,000 variations had developed into the structure we see today. Filaments where matter accumulated, voids where matter drained away. A web woven by gravity over almost the entire history of the cosmos. The largest known structure in the observable universe is called the Hercules Corona Borealis Great Wall. It's a filament estimated at approximately 10 billion light-years in length. That's about 1/10 the diameter of the entire observable universe. A single connected structure, possibly stretching across 1/10 of all we can see. Astronomers continue to debate whether the Great Wall is genuinely a single gravitationally connected structure, or whether it's a statistical fluctuation in galaxy density, and the debate isn't fully settled. But even on the conservative side, structures of half that size are well established. The largest filaments are, by any human comparison, beyond comparison. To get a sense of scale here, consider the relationship between objects we usually think about and these largest structures. The Earth is about 12,000 kilometers in diameter. The Sun is about 100 times that in diameter and 1,000,000 times that in mass. The solar system is roughly 100,000 astronomical units across, where an astronomical unit is the distance from the Earth to the Sun. Our galaxy, the Milky Way, is about 100,000 light-years across. The local group of galaxies, our gravitationally bound neighborhood, is about 10 million light-years across. The Virgo supercluster, of which our local group is a small member, is about 100 million light-years across. At each level, you go up roughly a factor of 100 or so. The filaments of the cosmic web are about 10 billion light-years long, so we're looking on the cosmic web at structures roughly 100 times larger than the largest gravitationally connected superclusters. We are, ourselves, very small things, sitting on a small rock, in a moderate-sized galaxy, near the edge of a medium-sized filament, looking out at a web of filaments and voids stretching across all the visible cosmos. Then there are the voids, the empty places. The Buta's void is one of the largest known voids in the observable universe. It's approximately 330 million light-years across, and it contains, by recent surveys, far fewer galaxies than the cosmic average. Maybe a few dozen, scattered across a region that, in normal density, would contain tens of thousands. If we lived inside the Buta's void, our view of the cosmos would be very different. We wouldn't see the neighboring galaxies that we currently see. We wouldn't see the local group structure we live in. We'd see in the immediate vicinity almost nothing. The nearest galaxies would be hundreds of millions of light years away, well beyond what we could see with the naked eye, and difficult to detect even with early telescopes. There's a thought experiment astronomers sometimes mention. If the Milky Way had happened to form inside the Buta's void, we would not have discovered the existence of other galaxies until the 1980s. The void is so large that the nearest galactic neighbours would have been invisible to telescopes of earlier eras. Imagine living inside that void. Imagine being a civilization developing astronomy with the assumption that your galaxy is alone. Imagine, after decades of careful observation, finally building a telescope sensitive enough to pick up the faint smudges of distant galaxies and discovering that you were wrong, that there are not just other galaxies but trillions of them in every direction. It's a fluke of where we are that we discovered other galaxies in the 1920s rather than the 1980s. We happen to live in a relatively crowded part of the cosmic web. The local group is right there, our neighbour Andromeda visible to the naked eye, the Magellanic Clouds visible from the southern hemisphere. The universe seemed full of structure because in our particular location it is. If we'd been somewhere else, our picture of the universe would have developed differently. The voids, by the way, constitute about 80% of the total volume of the observable universe. Most of space, even within the part we can see, is empty. The filaments and clusters where galaxies are concentrated are a minority of the total volume. They look dense in the maps because all the matter is there. But if you measured volume, most of the universe is the empty parts. The web's threads, the bright filaments are the exception, not the rule. Here's a way to feel the cosmic web, if the image is helpful. Imagine a vast spider web in 3 dimensions. The web is enormous, stretching in every direction farther than you can see. The threads of the web are bright. The spaces between the threads are dark, empty, vast. Where the threads cross, there are dense knots. These are the galaxy clusters. Each knot contains hundreds or thousands of galaxies, packed close together by gravity. The threads themselves are long strands of galaxies, hundreds of thousands of galaxies in each thread, stretched out along the line of the thread in patterns that look almost orderly. The empty spaces between threads are the voids. Most of the volume of the web is empty. The threads are thin compared to the gaps between them. You're sitting in a particular galaxy, which is in a particular thread, which connects to a particular knot. From inside the thread, you can see your local part of the web, other threads in the distance, other knots. The structure extends in every direction, as far as your view reaches, which is to say, to the edge of the observable universe, and then beyond. This is not a metaphor. The cosmic web is what computer simulations of the universe's evolution actually produce. When you run the equations of general relativity forward in time, starting from the tiny variations we measure in the cosmic microwave background, what you get is the cosmic web. The simulations match the observations to a precision that, to put it mildly, would impress any skeptic. The structure is real. The matter has organized itself into this pattern. We live inside the pattern. Or here's another way to feel it. Think about the floor of the ocean. Most people picture the ocean floor as relatively flat, with some mountains and trenches scattered across it. The actual ocean floor is a landscape of extraordinary structure. There are mountain ranges that go around the entire planet, the mid-ocean ridges, where new crust is being formed. There are trenches deeper than mountains at all, where old crust is being subducted. There are vast abyssal plains and isolated underwater volcanoes and complex regions where multiple geological processes have left layered evidence of long histories. The universe has the same character. From a distance it looks uniform. Up close, on the right scale, You see structure, mountains and trenches, filaments and voids, a landscape of extraordinary complexity, with us sitting on one small spot, in one filament near the edge of one knot. So that's the picture of where we are. A small rock in a moderate galaxy, in a filament of the cosmic web, in a bubble of probably infinite space, in a bubble universe that's one of perhaps 10 to the 500th, in a possibly mathematical reality that may include all consistent structures, each layer larger than the last by a factor that the human mind can't quite hold. That's a lot of layers. It's a lot of zoom out. In the next part of tonight, I want to come back to where we are, not where the rest is, to what it means to be here, in our particular bubble, on our particular rock, at our particular moment, because there's one more thing about our cosmological moment that's worth knowing, and it's the thing that makes everything we've talked about tonight even more strange. We're not just in a vast cosmos, we're in a vast cosmos at a particular time, and the time matters. There's a common assumption about science. It goes something like this. Science is the process by which we figure out the world. Slowly, sometimes painfully, often after detours and mistakes, we accumulate understanding. The arc bends toward more knowledge. The things we don't know today, we'll know tomorrow. Maybe not in our lifetimes, maybe not in our grandchildren's lifetimes, but eventually, given enough time, science will fill in the gaps. That assumption is true in some domains. In medicine, in materials science, in chemistry, in plenty of fields, the arc really does bend toward more knowledge. The diseases that puzzled doctors a century ago are largely understood now. The phenomena that scientists couldn't explain in 1900 have been explained by 2000 for the most part. There's plenty we don't know, but there's no fundamental obstacle to learning except time and effort and resources. In cosmology, the assumption breaks. There are things about the universe that we will never know, not because we haven't tried hard enough, not because the science is too difficult, but because the structure of the universe itself makes the knowledge inaccessible. The information is, in the most literal sense, beyond reach, and not just beyond our current reach, beyond any possible reach, ever, by anyone, for any reason. The cosmological event horizon is the cleanest example. We talked about this earlier. The horizon sits at about 16 billion light years from us. Galaxies beyond that distance are receding faster than light due to the expansion of space, and any light they emit now will never catch up to us. Galaxies inside the horizon, but close to it, are receding nearly as fast. Over time, more of them will cross. Here's the part that, when you think about it carefully, is striking. The horizon isn't waiting for better instruments. It isn't a problem of technology. No telescope will ever see past it. No probe will ever cross it. No future civilization, no matter how advanced, will overcome it. The horizon is a feature of how space behaves when dark energy drives accelerated expansion. The geometry creates the limit. The limit is permanent. The limit is structural. Imagine you're standing at the edge of an ocean. The horizon is, let's say, 15 kilometers away. That's where the curvature of the Earth carries the surface beyond your line of sight. If you wanted to see what's on the other side of the horizon, you could climb a hill. You could fly in a plane. You could go to a high tower. From higher up, you can see farther. The horizon is, in that sense, an engineering problem. You can defeat it given the right tools. The cosmological event horizon is not like that. There's no hill to climb. There's no higher vantage point. The horizon is created by the expansion of space, and the expansion of space is happening everywhere, in every direction, at the same rate. You can't get above it. You can't go round it. You can't accelerate to catch up with the receding light. The light isn't getting away from you because it's moving fast. The light is getting away from you because the road between you and it is getting longer, faster than light can travel it. Speeding up doesn't help. The road keeps getting longer. So the horizon is permanent. Some information is on the other side of it. That information is, in the deepest sense, lost to us. Not lost like a forgotten book, lost like a book that was burned, except worse, because no copy ever existed in any location accessible to us. And it's getting worse. The horizon doesn't just stay fixed, it's contracting relative to the universe outside it. Dark energy is accelerating the expansion. Each year, a few more galaxies worth of light slips past the boundary. Each million years, a few more chunks of the cosmic record become permanently inaccessible. By 150 billion years from now, all galaxies outside our local group will have crossed the horizon. By 1 trillion years from now, even the red-shifted echoes of those galaxies' last visible light will have faded below any detectable level. The history will be gone. A future civilization in our galaxy 1 trillion years from now would look out at the night sky and see something strange. They'd see the Milky Way's stars. They'd see Andromeda, which by then will have merged with the Milky Way into a single galaxy. They'd see the remnants of the local group. They would see in every direction what looks like an island of stars in a sea of nothing. No other galaxies visible, no cosmic microwave background detectable, no evidence of the Big Bang, no evidence of expansion, no evidence of the universe's full extent. The cosmology textbook they would write, based purely on what they could observe, would describe a universe consisting of one galaxy. And it would be wrong. They would be inhabitants of a much larger reality, but the evidence for that reality would be on the other side of the cosmological event horizon. They would have no way to know. The history of the cosmos that we have access to now, in 2026, would be unrecoverable to them. The patterns in the cosmic microwave backgrounds that tell us how the universe began would be too faint to detect. The supernovae in distant galaxies that revealed the accelerating expansion would have set beneath their cosmic horizon forever. Take a moment with that. There is a future moment in the actual unfolding of time when a civilization could exist in our galaxy, on a planet like ours, with intelligence like ours, with science like ours, and they would have no empirical evidence that the rest of the universe ever existed. They would observe their own galaxy and see what looks like all of reality. They might even develop reasonable theories of cosmology based on that limited evidence. And the theories would be wrong in fundamental ways, not because the scientists were sloppy, because the universe had taken its evidence away. We are in the lucky position of being able to see further, not because we're more capable, but because we exist earlier. The expansion has not yet erased the record. The galaxies are still visible. The microwave background is still bright enough to detect with reasonable instruments. The history is, for the moment, still legible. This is what I mean when I say the window is closing. It's not metaphorical. There's a specific physical process, the cosmological event horizon contracting in apparent angular extent, that is slowly removing information from any observer's possible reach. We are not at the beginning of the closing. The process has been going on since dark energy started to dominate, several billion years ago. We are catching the universe in a particular state. The state is not stable, it's gradually becoming less informative. There's a phrase that some cosmologists use, partly seriously, partly with a kind of dark humour. We are living in the best possible era for cosmology, not because we're great at it, although we're getting better, because the evidence is, right now, easier to access than it will be again. A few billion years ago, the universe was too young for there to have been enough evolution for civilizations to look at it. A few 100 billion years from now, the evidence will have been erased. We happen to be in the brief window where complex life can exist and the cosmic record is still readable. It's a window, it's not permanent. Old photographs do something similar on a much smaller scale. A photograph captures light that bounced off a person at a moment in time. The chemicals on the film record the pattern of the light over time. The chemicals degrade, the colours fade, the contrast softens, the fine details blur. Eventually, the photograph becomes unreadable. The person is still there, in some sense in the memory of anyone who knew them, but the photograph as evidence has become unrecoverable. The universe is doing this on a cosmic scale. The photographs of the early universe, in the form of the cosmic microwave background, are still readable. We can pull detail out of them, we can map them, we can extract numerical parameters from them. They're the best photograph we'll ever have of the universe's youth. In 1 billion years, they'll be harder to read. In 100 billion, they'll be effectively gone. There's another way the universe puts limits on what we can know, and it's worth talking about because it's different in character from the cosmological event horizon. The first one is about distance. This one is about time. The cosmic microwave background, the oldest light we can see, comes from 380,000 years after the Big Bang. Before that moment, the universe was an opaque plasma. Light couldn't travel freely. It scattered off free electrons constantly, and any photon trying to make its way out got knocked around so much that no coherent image could form. So the cosmic microwave background is the limit of how far back we can see optically. It's our oldest visible photograph. But the universe has a history before 380,000 years. The first 3 minutes when the elements were forged, the first second when the building blocks of matter formed, the first fraction of a second when inflation may have happened, the first 10 to the minus 36 seconds before inflation, when the conditions were so extreme we don't have working physics to describe them. We can't see directly into any of that. The cosmic microwave background is opaque to photons from earlier times. The plasma absorbed everything, so our optical view of the universe terminates at 380,000 years after the Big Bang. Anything before that is, optically, a wall. There are workarounds, but they're harder. Neutrinos, which interact much less with matter than photons do, could in principle escape from earlier eras. If we could detect the cosmic neutrino background, the way we can detect the cosmic microwave background, we could see back to about 1 second after the Big Bang. That's a much earlier view. The neutrinos exist. They're predicted by every working model of the early universe. We just can't detect them yet with current technology because their energies are too low. Gravitational waves, which interact even less, could in principle escape from the inflationary era. If we could detect the primordial gravitational waves, we could see indirectly into the universe's first 10 to the minus 32 seconds. We'd have evidence of inflation itself, of the moment when the universe was undergoing exponential expansion. There are experiments trying to detect these, but they haven't succeeded yet. They might, or they might not. Some models of inflation predict the gravitational wave signature would be too weak to detect. So even within our observable patch, there are limits on what we can know about the early universe. The photon wall at 380,000 years is hard. The neutrino window opens up the picture in principle. The gravitational wave window goes earlier still. Beyond that, the universe gets quieter. The first 10 to the minus 36 seconds before inflation may be permanently beyond our reach. We don't know what the universe was like before inflation. We have models, we have speculation, we don't have evidence, and we may never have evidence. There's a third kind of limit, and this is the one that's hardest to talk about because it's the most abstract. If the inflationary multiverse picture is correct, there are other bubble universes with other physics scattered through an exponentially expanding space. By construction, those bubbles are causally disconnected from ours. We can't see them, we can't communicate with them. They might as well not exist from our point of view, except of course that they do. Now ask the question, is the multiverse a falsifiable theory? Can we test it? In some sense, yes. We can test the underlying physics, the inflation models, and the string theory models that predict the multiverse. If those models hold up to experimental scrutiny on the parts we can test, that's evidence, indirect but real, that the predictions they make about other bubbles are also correct. But we can't directly observe another bubble. Not now, not ever. The evidence will always be indirect. Some philosophers and some scientists find this troubling. They argue that a theory whose central claim is unobservable isn't really science. Other physicists and other philosophers push back. They point out that we accept all kinds of unobservable claims as science, as long as the broader theory they belong to makes testable predictions in other ways. Atoms were unobservable for centuries, but atomic theory was good science long before we had microscopes that could resolve individual atoms. Black hole interiors are in principle unobservable, but black hole theory is good science because it predicts plenty of testable things outside the event horizon. The multiverse in the inflationary picture falls into a similar category. The other bubbles can't be observed, but the theory that predicts them can be tested in other ways. Inflation makes specific predictions about the cosmic microwave background. Those predictions have been confirmed, repeatedly, to high precision. String theory is harder to test directly, but it has internal mathematical constraints that are very tight. The combined picture isn't certain, but it's not nothing either. Still, the multiverse, if it exists, is largely unknowable. We can know it exists indirectly, but we can't know much about what's in it. The 10 to the 500 vacuum states of the string landscape are mostly inaccessible to investigation. We can describe the landscape mathematically, but we can't pick any particular other bubble and study it. The other bubbles, even if they exist, are functionally outside the domain of empirical science. They're part of reality, in some sense, but not the part we can do experiments on. This combines into a picture then, that's worth sitting with. There are layers of unknowability built into the universe. The cosmological event horizon, the photon wall at 380,000 years, the other bubbles of the inflationary multiverse, each one a different kind of barrier to knowledge, each one structural, not technological, each one permanent. This isn't a failure of science, it's the shape of the universe science is trying to know. We're not at the beginning of asking these questions. People have been asking them for decades. We're at a moment where we can articulate what we don't know and why we can't know it with more clarity than ever before. That's its own kind of progress. Here's the thing I want to say plainly, because I think it matters. Some people, when they encounter this material, react with a feeling of futility. If we can't know everything, what's the point of knowing anything? If the universe is going to take its evidence away, why bother piecing together what we can? If there are other realities we can never visit, why think about them? These are real reactions. They come up, they're worth taking seriously. But I think they miss something. The fact that there are limits to knowledge doesn't make the knowledge we have less valuable. If anything, the opposite. The fact that we know what we know is more striking when you realize how much of it could have been hidden but isn't. We have a window. The window is open. The window is, by cosmic standards, brief. And while it's open, we can see things that no observer in the future will be able to see ever again. Take the cosmic microwave background. We can see it, we can map it, we can pull from it the parameters that describe the entire history of the universe, the age of the universe, the geometry of space, the composition of matter and energy, the age of the cosmos when atoms first formed, the age when the first stars lit up, the detailed history of structure formation, all of that encoded in a faint hum of microwaves filling the sky, available to anyone with the right instruments. Compare that to a civilization in our galaxy 150 billion years from now. They wouldn't have the cosmic microwave background available in any usable form. They wouldn't be able to read any of those parameters. They could measure their local environment, they could study the stars in their galaxy, they could deduce some things about the history of their cluster. But the deep history of the universe would be beyond them. We have something they won't have, whether or not anyone notices. It's worth pausing on the asymmetry of cosmic time here. The universe is 13.8 billion years old. Stars have been around for most of that time. Since about 200 million years in, heavy elements have been accumulating through generations of supernovae for the last 12 or 13 billion years. Life, on Earth at least, has been around for about 4 billion years. Complex life for maybe 600 million, anatomically modern humans, about 300,000 years. Recorded history, about 5,000. Modern cosmology, about 100 years. And we happen to be looking at the universe now, not because we chose to, because we happen to evolve into a position to look at it. And the moment we're looking turns out to be one of the better moments to be looking. The universe is old enough to have produced everything we are, young enough to still be telling us how it began. It's a coincidence in some sense. We didn't time it, but it's a useful coincidence. You can react to that with any emotion you want. Gratitude is one option. So is curiosity. So is a kind of quiet attention to what the universe is showing us before it stops showing it. The window is open. We have the records. We have the photographs. We have the radio echoes. We have the data. We are not at the end of anything. We are not at the beginning either. We are somewhere in a long sequence of cosmic moments, with this one being a particularly informative one, and we happen to be here for it. So when you go outside on a clear night and look up at the stars, here's what you're actually seeing. You're seeing photons that left their sources tens, hundreds, sometimes millions of years ago. You're seeing the light that was emitted, that traveled through the expansion of space, that made it through the interstellar medium, that survived dust and gas and the long journey, and arrived finally at your eye. The fact that it arrived at all is in some sense an accident. The universe could have stretched faster, the dust could have been thicker, the photon could have been absorbed somewhere along the way. It wasn't, it got through, and now it's in your eye, telling you something true about something far away. That photon will not be available to a future observer in the Botha's void. That photon will not be available to a far future civilization in the local group after the expansion has taken its information away. That photon is reaching you now because you're in the right place at the right time. The universe has, for a brief moment, made itself legible. You're not just looking at the stars, you're reading the universe's library. The library is open this evening. It will be open for a long time yet, by human measures. But on cosmological timescales, it won't be open forever. The doors are slowly, gently closing. The books are slowly, gently being moved beyond the shelf you can reach. You happen to be a reader during the time the library is still well stocked. That's what tonight has been about, in a way. The size of the library, the strangeness of what's in it, the fact that we have access to it, and the fact that our access is, by the universe's own design, gradually being taken back. So we've come back to the edge of the map. We know now what the cartographers didn't say. The map is not shrinking, our ability to read it is. And the candle, remember the candle from earlier in the script, the pool of light around you that lets you see the room you're in. The candle isn't going out, the candle is still burning. The candle just doesn't reach as far as it used to. The walls of the room are still there, they haven't moved. The candle is gradually losing its grip on the edges of what it can illuminate. Slowly, the walls slip back into darkness. Slowly, the lit area shrinks. Not because the candle is failing, because the room is in some sense getting larger. Here's what we know. The universe is at least 93 billion light years across in the part we can see. It's almost certainly much, much larger in the part we can't. It's almost certainly flat, and almost certainly close to infinite. If it is infinite, then somewhere out there, in a configuration of matter that's exactly identical to this room, there's a copy of you listening to a copy of this voice. There are infinitely many such copies. There are infinitely many copies that are almost like you, infinitely many that diverge in small ways, infinitely many that have lived your entire life so far and will continue to do so for the next breath, but not the breath after. Beyond our bubble, if eternal inflation is correct, there are other bubbles with other physics, other arrangements, other possibilities, maybe 10 to the 500th of them or more. Beyond that, if the mathematical universe hypothesis is correct, There are all consistent mathematical structures, realities we have no concept of, structures that don't even fit into our category of universe. And all of it is, for the most part, inaccessible to us. The cosmological event horizon blocks the far reaches of our own bubble. The bubbles of the multiverse don't communicate. The mathematical universes, if they exist, are accessible only through pure thought, not through experiment. Our view of reality, even when we're looking as hard as we can, is constrained. And here, in our particular bubble, in our particular galaxy, on our particular rock, we have a brief moment in cosmic time when the records are still readable. The cosmic microwave background still hums. The distant galaxies are still visible. The pattern of the structure is still measurable. The view is good. The view will not be this good forever. We are, somehow, here for this. Briefly, quietly, looking up, trying to figure out what we're inside. That's not a small thing. That's actually one of the larger things that has ever happened in any part of the universe we can confirm. We didn't choose to be here. We didn't arrange the timing. We just are somehow doing this, looking at the cosmic web, mapping the galaxies, reading the radiation, writing the equations, wondering on a small planet why the universe is the size it is and what it means that we can almost answer that question. That's where I want to leave us before the last reflection, sitting with what we have, knowing what we don't have and might never have, knowing that the window is open for now, knowing that the universe is much bigger than we usually think it is, knowing that we are in some real sense here for the looking. There's one more thing I want to say before we go into the closing. It's about scale and how human beings handle it. When you're told the universe is 93 billion light years across, your brain does something funny. It doesn't really process the number. It substitutes a feeling for the number. The feeling is something like very big, maybe a touch of awe, maybe a touch of vertigo, but the actual number, the actual size, doesn't get represented in your head because there's no room for it. Brains evolved to deal with the sizes of predators and prey, and rivers and mountains. The sizes that mattered for getting through a day. The cosmic sizes are simply outside what the equipment can do. This is true for every large number in this script. The 2 trillion galaxies, the 10 to the 500th vacuum states, the 10 to the 10 to the 29th meters to the nearest copy of our observable universe. Your brain doesn't represent any of these. It hears them, lets them sit for a second, and substitutes a feeling. Sometimes the feeling is wonder, sometimes it's just a kind of static. The number as a number doesn't fit. That's not a failure of imagination. That's the equipment we have. We didn't evolve to grasp cosmic scales. We evolved to count maybe a few hundred things at most, and to feel quantity by what we could see, hear, taste, hold. Cosmic numbers are outside the operating envelope. They have to be handled by symbols, with the symbols doing the work that the intuition can't do. This is why analogies are useful, but only up to a point. A road trip can give you a feel for 1,000,000 miles if you stretch your imagination. A stack of pennies can suggest a few billion. After that, the analogies start to break, and after a certain point they don't help anymore. There's no analogy for the number of vacuum states in the string landscape that's actually helpful. The number is just too far outside the envelope. So when you hear, in a script like this one, a phrase like the nearest exact copy of you is at 10 to the 10 to the 29 meters away, you don't really know what that means. Neither do I. Neither do the physicists who write the papers. We can work with the numbers, we can manipulate them, we can verify they make sense within the broader theory. We don't grasp them in the way we grasp the distance to the corner store. The grasping isn't possible. The number lives in symbolic space, not in our heads. That's worth knowing because it tells you something about your relationship to this material. You're not supposed to walk away from this with a clear picture of the multiverse. The multiverse, if it exists, is not picturable. You're supposed to walk away with a slightly altered sense of where you are. Knowing that the picture you carry is a small one. Knowing that the actual cosmos is much larger than the picture suggests. Knowing that the picture, useful as it is not the territory. That's what the edge of the map has been about this whole time. The map you have is the picture in your head. The territory is the actual universe. The map and the territory are not the same. The map is small. The territory, by every reasonable inference, is enormous, and maybe infinite, and maybe infinitely repeated, and maybe one bubble in a vast landscape of other bubbles, and maybe one mathematical structure in a vaster space of all consistent structures. You can't picture any of that. You're not supposed to be able to. You're supposed to know, somewhere in the back of your head, that the picture is small, that there's more beyond the picture, that the edge of the map is not the edge of the world, that the cartographers, including the modern ones, have done their best, and their best produces a map that is by any reasonable measure an enormous achievement, and also by any reasonable measure an enormously partial one. We've been working with that idea this entire time. The 93 billion light-year bubble, the cosmological horizon, the flat infinite cosmos, the bubble universes, the copies, the mathematical structures, each one a layer of the answer, each one beyond direct verification in most ways, each one supported by some combination of mathematics and inference and the parts of the picture we can check directly. And here we are, at the edge of one map, holding what we have, knowing the map is partial, knowing the territory continues, knowing we are somehow in a position to know that the map is partial, which is itself a kind of accomplishment. Let's stay here for a few more minutes, not adding new facts, just sitting with what we've talked about, because the material in this script is the kind that benefits from a little time, after you've heard it, to settle. Here's what I think is the strange thing about the modern picture of the universe. It's not just that the cosmos is large. People have been telling us the cosmos is large for as long as people have looked up. The Greeks knew it was bigger than they could measure. The medieval philosophers wrote about it with a kind of awe that was also a kind of resignation. 19th century astronomers, when they realized our galaxy was a galaxy and not the whole universe, struggled to keep their composure. The size of the cosmos has been growing in human imagination for a long time. That's old news. What's new in the last 100 years, and especially in the last 40, is the structure, not just bigness, architecture. The fact that the universe isn't simply enormous, it's organized, it has features, it has a history, it has a geometry, it has an age, it has, embedded in its earliest light, the signatures of processes that happened in a fraction of a second, processes whose marks we can still read now after 13.8 billion years of weathering. That's what's new. The universe used to be a vague, dark, immense thing beyond our reach. It's still beyond our reach in most ways, but now we know what it's made of, in broad terms. We know how old it is, to within a fraction of a percent. We know the relative amounts of dark matter and dark energy and ordinary matter to a couple of decimal places. We know what the early universe looked like in spatial detail. We know the rate at which it's expanding and the rate at which the expansion is accelerating. We know the geometry to within 0.4%. A century ago, none of this was known. None of it. The universe was a question mark with a few stars in it. Now it's a structure with measured parameters, with a history we can sketch out, with mechanisms we can name. The leap from then to now is by historical measures sharp, and we accomplished it in roughly 100 years using a species worth of accumulated effort with telescopes and satellites and computers and patience. That doesn't change the size of the universe. The universe was already this big, we just didn't know. What changed is that we built ourselves into a position where the size becomes something we can talk about somewhat clearly, rather than just gesture at. And that position, the position we're in now, is itself temporary. We've talked about why. The cosmic horizon is closing, the information is being moved out of reach. we're not at the end of cosmology. We're at a moment when it's particularly possible to do cosmology well. The moment will pass. Not soon by any human measure, but the moment will pass. So if you want one summary of what's strange about being alive right now, it's this. You happen to be one of the things the universe produced, briefly, during the period when the universe is most legible to itself. The thing you're doing, right now, listening to a voice talk about cosmology, is something only a very small slice of cosmic history allows. Earlier than this, no stars, no chemistry, no creatures to listen. Later than this, no clear view of the universe, no microwave background to detect, no understanding of how things got the way they are. Between those two limits, a window. We're inside the window. You, listening, right now. The number of moments in cosmic history when an observer could exist at all, let alone exist with our particular capabilities, is a small fraction of the total. And we happen to be in one of those moments, not by choice, by the way things have worked out, in our particular bubble of the inflationary multiverse, on our particular planet, in our particular galaxy. We're here for the looking. I find that worth pausing on, not in a way that makes anything mystical, in a way that's just factually accurate. The universe is much larger than the human imagination can hold. We are very small things in it, and we happen to be here, looking, at the time when looking is unusually possible. That's what's going on. And here's what you know now that you didn't know 2 hours ago. The 93 billion light years, that number people quote when they want to gesture at vastness. It's the view from the bottom of a well, a very beautiful, very deep well, and beyond the well's rim, more universe, possibly infinite, certainly far larger than anything that number suggests. Bubble universes where the laws of physics are different, where the strong nuclear force is a little stronger or a little weaker, where stars never ignited, or where something we have no word for happened instead. And somewhere in an infinite flat cosmos, configurations of matter repeating, not probably, mathematically, including this one. We are brief things, warm things, here for a sliver of cosmological time so small it doesn't have a useful name, and we happen to exist at the precise moment in cosmic history when the evidence for all of this is still visible, when the light from ancient galaxies has not yet crossed the horizon, when the cosmic microwave background still hums faintly in the background of everything, when the universe is old enough to be interesting and young enough to still be legible. You know now that the map is not the territory. You know that the edge of the map is real and physical and permanent. And you know that we're not at the end of anything. Here's the question I'll leave with you. If there are infinite copies of you out there, each one certain they're the original, what makes you think you're different? Sleep well.